Okay, great. Welcome back, and thanks a lot for the invitation. And this is my first LISA symposium, so it's great, everything great. They asked me to talk about extreme mass ratio spiral and basically everything beyond vacuum and beyond GR and the Ringdown. So it's a lot of stuff. I mean, make yourself comfortable. I just prepared some slides. I mean, 3-4 hours should be enough, I mean, to cover everything. Okay, of course, since I cannot cover everything, this is going to be a sort of personal view, although, I mean, I really want to give you a glimpse of some specific science cases that have been taken by very wide community. And indeed, this is a bit a complementary talk with the one that Nico gave 2 days ago. And he gave me the inspiration, I mean, to make this cloud, and just to state how many people worked. Basically, there are 100 names here, and I wanted to make more, but the website just stopped me. So there were at least 100 names, and I mean, the collaboration is very large, and we have produced, I mean, a lot of super interesting and very physics-rich works in the last year. So Nico, 2 days ago, talked about fundamental physics and the motivation and why it's important. I just want to restate again a couple of things, and which are related to beyond, so gravity test and the environmental. I mean, we have, especially with extreme mass ratio spiral, sources, new sources that, besides some very exotic case, won't be observed by ground-based interferometers. So we have new sources with new mass scales on new dynamical regimes, and this basically offers new opportunity to test pillars of GR, like how gravity works in some unexplored regime. And we also have a very, very specific case into the environment, because we know that whatever we believe, I mean, binaries don't evolve in vacuum, and actually we know that there is something, whatever the paradigm is, which is dark matter. So when you have these two things here, basically you are exploring new regime, you're exploring new physical phenomena, and now there are at least two clear things. One is fundamental physics, and the other one is systematic. So trying to understand, so everything that Adam and other people, for example, are preparing for us is good enough, and so avoid contamination from other unknown effects. Both of these things come from a fairly equal amount of opportunities and problems. Okay, last slide of introduction is why EMRIs, why extreme mass ratio spirals. And there are different reasons. I just want to point out one, which is that they are particularly good in constraining some particular low frequency effect. So this is a plot that I've taken from a paper by a student by Nico. And let me state that it's very difficult for extreme mass ratio spiral to have constraint or analysis which are realistic, in the sense that use state-of-the-art gravitational waveforms free of systematic, because I mean, we have seen with Adam that it's already as difficult as possible to get these waveforms in GR. So almost everything I'm going to present today is basically based on approximation, or, as in this case, extensions, extrapolations from the PN-based analysis, which are actually very helpful. And indeed, I think that the community, given the variety of science cases, is still a bit navigating on the most important science cases and how to construct realistic waveforms. However, this is an analysis that basically takes, it's an agnostic analysis, so basically takes the waveform in GR and then add diagnostic shifts, and you can try to constrain how it's going to be like the constraint on this parameter beta, which is the agnostic shift, and the parameter B controls the PN order, the post-Newtonian order of this deviation. Basically, negative are fx more important at low frequency, higher are fx more important at high frequency, and here there are different sources. And you see that at low frequencies there are EMRIs, which are doing very, very good, okay? So because of the large number of cycles spent in a genuine low-frequency regime, extreme mass ratio spirals are particularly good in constraining low PN orders. Now, when you constrain beta, then you want to map this beta into a specific model, which basically means turning this constraint into the coupling of your beyond GR theory, the density of your M vacuum, or whatever is parameter of your specific science case. And this is crucial. It's crucial that there are theoreticians developing physical model, because then this map tells you whether the agnostic constraint actually turns into realistic physics that can be constrained by Lisa, and I'll give you some example. And this is, for example, a work done with Vitor some years ago, in which we basically map this beta into an environmental effect, which is gravitational drag. So it's an effect of a resisting force that acts on the lighter component of an EMRI when basically it's in a medium, and different sources. These are stellar mass sources, and here let's look at Lisa. Now you see there are different sources. This is basically the smallest density that you can distinguish from zero, so from vacuum. These are different sources like massive black holes, intermediate mass Redshift spiral, extreme mass Redshift spiral, intermediate mass binary black holes, and you see that extreme mass Redshift spirals, or in general asymmetric binaries, are doing very, very well. Okay, how do we study extreme mass Redshift spirals? So, like in general, extreme mass Redshift spiral, the narrative beyond extreme mass Redshift spiral always been like that we're going to use them to test the space-time of the central object. Okay, this is extremely difficult because, as Adam has shown you, basically self-force theory in general works in perturbing the background space-time. But I mean, the real problem is that if you want to perturb something, you need that something, and it's extremely difficult to have like a background beyond vacuum GR, which is reliable for this kind of job. I mean, we have seen in some parallel session with Nico's student, but there are some cases, and I want to spend a few minutes in this, in which this is not needed, okay? And in some cases, actually, the background space-time doesn't really play any specific, or actually deviations from the background space-time doesn't really play any specific role, and everything just comes from the light and secondary. And this is actually extremely helpful, because then it gives you a lot of things for free, and you can immediately apply things that Adam showed. And this is actually something that Nico talked already last time. So this was a work that we did with Thomas Sotirio and other people. Basically, we try to ask ourselves what you can do, how you can actually build realistic models that you can immediately use to make forecast on parameter estimation on a cluster beyond GR model. So this is basically Einstein theory plus like some scalar field, no minimally coupled to gravity. Now, and this covers a lot of theories, and they have the feature that this alpha is a dimension full parameter, which has dimension of length square. So in physical units, basically this is an action that has an effective field theory cutoff. So you actually have interaction suppressed by some energy scale. And in these theories, black holes have charges. So these charges basically tells you how much there is the deviation in GR. And these charges scale as alpha divided by the mass of the object. Okay, some powers. And you can understand that if you have a very massive black hole, the charge will be very, very small, while if you have a stellar mass object, the charge will be very, very light, very, very large. Okay? So this actually allows to decouple the system because of the deviation, because the charge of the massive black hole will be very, very small, and so you can actually treat this guy as pure Kerr, and the charge of the lighter object will be actually large, okay? And so you can do perturbation into a Kerr black hole as in GR, and everything will be controlled by the charge of the secondary, which is going around, is acting basically as a charge going around in the space-time and modifying the prediction. Now, everything of this was actually put in a self-force context by Andrew Spires, and basically that was able to cast all the framework in order to fit this within the self-force approach. And if you basically use this formalism, you see that at the adiabatic order, the one that Adam was discussing today, basically the problem of beyond GR and extreme mass Redshift spiral just cast into solving the usual Astor equation that you will have in vacuum GR plus a scalar field. Okay, this has been solved since the 55, 57, so we have fluxes and table for everything, and then you have to solve just this equation here, and the scalar field contribution just comes on top of the gravitational self-force contribution, which basically means that you have waveform for free, because the amplitude are given by this guy. The only things that will change are the total fluxes. Okay, Andrew actually made step forward, so basically he went also to the second order, and it works the same. So basically in this approach here, where it's the lighter component introducing deviation, you can actually add the correction even at the self-force, at the second order in the self-force. Now, this is very powerful and very easy to work with, and indeed, basically, Lorenzo Speri introduced basically waveform generated in this way within fast EMRI waveform, which is a standard tool to make now analysis with extreme mass Redshift spiral. And so we made Bayesian analysis, and these are the constraints. Basically, you can get the numbers really don't matter on the scalar charge, which the scalar charge of the secondary. And so you see basically how this basically has been produced using waveform which are exact adiabatic order. So these are almost at the state of the art. Okay, and this is, for example, in this formal is the state of the art of the waveforms that we have, like in GR and in beyond GR, that have been implemented in fast memory waveforms. Okay, and then actually everything that I've said so far is purely agnostic, so the constraint depends on the scalar charge T, but I mean, then this charge can actually be mapped in a specific model, in a specific theory of gravity. This is one of the theories that yesterday Nico talked about, is Gauss-Bonnet gravity. There is a relation between the scalar charge and the fundamental coupling of the theory, this alpha. So whenever you can actually put a bound on D, then you can actually translate that constraint on alpha, and this is what Lorenzo did in this paper, so turning the constraints on the scalar charge to the constraint on the coupling cost. Okay. This thing can actually be extended to the massive case, because I mean all the previous stuff was basically made for massless scalar field, and this is really great. This was an example carried by Susanna Barsanti, now postdoc at Nottingham with Thomas Sotiriou, where basically showed that Lisa can actually put for scalar field, for massive scalar field, can put simultaneous constraint on the mass of the scalar field and the charge of the lighter objects. So these are like constraints obtained with the adiabatic, so like fully realistic waveforms for extreme mass ratio spiral and just for Lisa. Massive fields are extremely interesting because they provide a series of new phenomena like floating orbits, and this is a plot taken by a paper by Nico, Vitor, and Paolo Pani. So basically when you have massive scalars, you can have new phenomena appearing, and for example, like basically the scalar field contribution can cancel out completely the gravitational wave emission, and so the binary just decelerate and can stall at some orbits. Okay, let's go now back to the primary, because the community has developed a lot of work to test basically what is called the non-careness of the primary. So most of the activity, or the vast majority of the activity, has been devoted to study deviation is what is called like the multipolar structure of the central object. So if you take exotic compact objects that have been proposed last year as alternatives to black hole and to test the nature of Kerr, these exotic compact objects have a multipolar structure which is different from Kerr, which is only dictated by the mass and the spin, and people have tried to study if Lisa can actually constrain these deviations, and this is a work by Gabriel Piovano here in the room, which basically tried to assess the detectability by Lisa observation of extreme mass ratio spiral of this guy here, which is called the love number. Now, the love number is mostly famous for neutron star binaries. It was measured by LIGO and Virgo, and it basically tells you the deformability property of an object, and tells you information of the star equation of state. Now, we have a very precise theoretical prediction in GR, which is basically that love number of Kerr black hole at 0. So whenever you find confidently that this guy is not 0, you may actually have hints of new physics. And Gabriel here tried to understand the constraints, the accuracy with which you can measure this parameter, and the accuracy is actually fantastic, because with Lisa you can measure these love numbers. I haven't put here numbers which are like 3-4 order of magnitude better, even with the love numbers that you can measure for neutron star with ground-based detector like the Einstein telescope. This is another work that has been done by Lisa Maggio. And basically, if you have this exotic compact object, you can actually have some new phenomena like resonances in the fluxes. So this is the fluxes emitted by an extreme mass ratio spiral, and in particular, the red one is shows that when the lighter component of the extreme mass ratio spiral hits some particular orbital frequency, which corresponds to the oscillation normal modes of the central object, you have these resonances which enhance the gravitational wave emission, and so are expected to provide basically distinguished features within the gravitational wave emission, which are different from the vanilla vacuum GR case. Okay. We're talking about primary and of scalar fields. So let me use the scalar fields to highlight, to move, to make the transition to the environmental part, because scalar fields are also considered as a proxy, for example, for dark matter, for what is ultralight massive fields, are good candidates to describe like the core of dark matter in the galaxies. And in particular, a lot of work has been done on ultralight bosons that can actually condensate around black hole through some phenomena phenomena, which are, for example, accretion or superradiance. And these which are called like gravitational atoms for similarities in the math and in the physics with the hydrogen atom, have some peculiar effects. And one of these is the ionization that was studied in some of this work here. So basically, you have this extreme mass Maselli spiral, and when the distance between the object gets comparable with the size of the cloud, so that it's evolving around the black hole, you have a process which is very similar in something that happens with the hydrogen atoms and other quantum effects, which is ionization. So basically, the EMRI, the lighter component, allows a transition between bound and unbound states, and you basically have that the scalar field clouds get detached from the black hole. This effect is very powerful. It exchanges energy between the cloud and the binary, so you would expect that the orbital evolution of this system would be considerably different from vacuum. And this effect is very, very strong. Here you see the emission, the radiated power in this ionization process and in the gravitational wave. And you see that in some zone, the ionization-like emission can be extremely large, way larger than the gravitational wave. In the last years, there have been like a considerable amount of work in this particular setup, and in here I'm reporting some works by Richard Brito and his group and by Francisco Duque in this room that basically have provided the first relativistic description of the evolution of this system. So an EMRI evolving in a scalar cloud that could be like some fuzzy dark matter model. And all of these, the real point, besides the number of the flux, is that you have in general, in this particular model, new features which are very distinctive, like resonances or sharp cutoff in the fluxes, which allow you to disentangle these effects from what you would expect from vacuum GR. Okay, let me talk about spikes. We are talking about scalar fields and dark matter, and let's focus a bit on dark matter. So there are numerical simulations that date since the 90s, basically, that if you take a reservoir of dark matter and you put like a black hole on the center, you're going to get basically what are called like a sort of, an adiabatic accretion, at least in first principle. So you get basically the dark matter accretes onto the black hole and creates spikes, okay? These are extremely important, I would say, for the detectability of this effect in the context of extreme Maselli spiral, because you create overdensities which are very, very important in order to promote their effect within gravitational wave emissions. And this is, for example, like the spikes generated and computed by Nicolas Pini in the group of Emanuele Berti at the Johns Hopkins in US that show basically the form of these spikes, and here, I mean, you will get the plateau of the dark matter density. Now, these are extremely extremely important because they allow to basically spot dark matter effect. So the overdensity allow to prompt or highlight the dark matter effects in the evolution. And here, I'm taking like two plots from this paper here, which basically show the dephasing that you will get from the vacuum case. So the evolution of a binary system in vacuum and the evolution of a binary system in a spike. And this is the difference in the number of cycles that you will get. And basically, the pink and the violet are two different models of dark matter, but basically there is a large number of dephasing that you get with the binary evolving. And here is the mismatch. So the mismatch is basically tells you how much two waveforms are distinct each other, and this is a mismatch between like a vacuum template and a dark matter template, and you see actually how the mismatch decrease if you include basically the dark matter spike with respect to vacuum. Now, this spike is so nice, it's so important, so rich of physics that some years ago the group of Vitor Cardoso basically developed a fully numerical approach to actually describe like the appearance, like fully relativistic black hole solution in a rotating case, including like the effect of the spikes. So this model was actually developed for different dark matter halo, for example, the Navarro-Franken-White and the Ehrenquist and the Inasto model. And if you have a fully relativistic black hole background with a spike, so a dress of dark matter, you can then evolve EMRI. And indeed, and then you can compute again, like things like the phasing and faithfulness, and see if there are differences in the orbital evolution with respect to the vacuum case. And here you see, for example, like this model models basically mostly depend, the difference with vacuum are mostly characterized by this guy here, which is the compactness of the halo. So basically it tells you the ratio between the mass of the halo and the length scale of the halo around the black hole. And for different values of the compactness, you see that the dephasing with respect to the vacuum case and in EMRI evolution, and this can be huge. I mean, for some particular case, you can have hundreds or tens of orbital cycles loss if you compare like the vacuum case with the dark matter spike. But I mean, the physics of these things is extremely richer, and I think this is where, I mean, everything gets extremely exciting. Here, what you see is for a black hole of this kind, so a black hole surrounded by a dark matter address, you see its response to an external perturbation. And this line here are like the gravitational perturbations, so gravitational waves if you want, and these one are fluid modes, okay? So because together with the usual gravitational modes, now you have also a fluid, so the dark matter, and this also will oscillate. And there is like the usual quasi-normal mode excitation here, but then you have a very slow decay, which is dictated by the exchange of energy between the fluid and like the gravitational sector. So basically this plot here tells you that the physics is very rich because there are the fluid modes and the gravitational modes which are talking each other and are exchanging energy. So the richness of these systems, I mean, is very large. Okay, and I'll come to my last science case, which are accretion disks. I just want to point out this work by Lorenzo Speri that came last year, although there were many others like even before, I mean, highlighting the relevance of this science case. So Lorenzo and other collaborators asked basically this question: if I have like an EMRI evolving in an accretion disk, so the secondary in general, well, we'll experience a lot of effects, but what they focused in this case was the torque induced by the mark, by the matter around. And what they try to do if to understand where Lisa could actually capture this torque through a different evolution of the binary during the spiral. These are two plots taken from the work by Lorenzo. And the main message is this plot here basically is an analysis in which you inject a vacuum template and then you try to recover this with a gravitational wave signal that has a torque modeled inside this, and the torque is modeled in this way here with an amplitude and then a power law in the radius, and the power law carries this coefficient that if you wish can be mapped into a sort of post-Newtonian expansion, so a negative Pn term. And here are the constraints that you will get on the amplitude. They consider two different models of accretion disk, the type beta and type alpha. Really, it doesn't matter too much. But you see that, I mean, the amplitude can be constrained for like canonical EMRIs. These were like 10 to 50 solar masses with a black hole of 0.9. And this instead is a plot in which Lorenzo basically injected a value as a gravitational signal carrying like information of the accretion disk and try to recover this with a proper template, including matter effect. And so the basic message is that torques can be detected, and that if you have a physical model, you can actually reconstruct the parameters. So basically, for example, the amplitude of this torque. Very nice. Okay, I have 1 minute probably to talk about the last two slides, and then I'll leave with that, and are contaminations, okay? So what about if you have multiple effects? Because, I mean, if you, again, you are in an accretion disk, you may expect like to have tons of effects, not only like the torque, but accretion and whatever, or just like in this particular case studied by Laura Sakuski and collaborators, they just took an accretion disk and then a dark matter spike that you could basically have simultaneously in the evolution of the binary. You could ask yourself, can we distinguish between the two? And I mean, apparently this is the results of their analysis, yes, because basically the different environmental effects may actually play a role in different stages of the environment. And so the evolution of the binary basically means the frequency sweep or the rate of change in the orbital radius will actually be different if you look at early times or at late times, where maybe the accretion disk would dominate instead of the spike, and vice versa. These people here, Pippa Cole and people of the group of Gianfranco Bertone, actually went a bit farther. So they actually did some Bayesian analysis trying to understand if you can actually, through bias factor, try to if you can distinguish like 3 different effects. So the effect of the spike, the accretion, and the gravitational atom. So basically what they did is I inject one signal, for example the spike, and I try to recover this with the other other waveforms, so a waveform that has accretion or a waveform that has gravitational atom, okay? And apparently, all of these have very, very large bias factor, so these are power logarithm of 10, which basically means that apparently the effects are all well distinguishable each from the other. Last slide, and the bias, which again is a bit related to what we've seen before. So these are a lot of Lorenzo's pair in this talk. These are two talks taken by works of Lorenzo, and it's actually just to close the circle, because we're talking about accretion disk, and we're talking about scalar fields, so these are taken from like works that I've discussed before. The question here, what happens if the signal inside your noise is given by a system in an accretion disk or by a non-GR theory, and you try to recover this with a vacuum GR template? Will the other parameters, the masses or the spin of the black hole, will be biased by using the wrong template? And you see there is a bias. Basically, in this case, for example, this is the posterior distribution that you will get using the right template, and this is the posterior distribution that you will get using the vacuum template, and this is the true value. And you see that there is a bias. And there is also a bias if, in beyond GR case, you use a GR waveform. But the bias of the intrinsic parameter looks extremely small. The scale here is 10 to minus 4. So instead of center, you would get like an error of 2 point something, 10 to minus 4. And the same on the spin on the black hole. So in both cases, basically, it looks at the message is that if you misinterpret like the signal with a vacuum or a GR template, you won't give too much damage in terms of like astrophysical conclusions, so the value of the masses and the spin, but this will be extremely relevant because you would induce small bias that probably will correlate if you are looking for small deviations like non-vacuum or beyond GR shifts. Okay, that's it. I think I'm running over time, so I can just leave with that.
Thank you very much. Questions? It's over there, question.
Hey, Andrea. Thanks for the talk. I have a question about the plot of the last slide. So here, why the Beer's uncertainty is smaller than the unbiased?
Sorry, say it again. The uncertainty is smaller?
The uncertainty, that is in this plot,
yeah.
There's the biased uncertainty of the unbiased result. It seems like smaller than the unbiased. What's the reason?
Of the uncertainty of the bias?
Yes.
I think maybe just because you have less parameters, so the correlations.
Okay, so both cases?
Yeah, in both cases, yeah.
Okay, thank you.
Further questions? Seems not to be the case, then everything is clear. Then, over there, yeah.
So in EMRI, because we will not have a clear merger, and you only have in spiral. So if you can we detect this signal as we are measuring them, or like can we do it after the fact, after post-processing data, or we can also do it on the fly? This kind of environmental effect analysis for EMRI. Do you have some opinion about that?
So you're asking whether you can detect this effect live or in post-processing?
Yes.
I think, I'm not completely sure because I'm not an expert of that analysis. I think that for very large deviations, if you don't use the proper template, maybe, I don't know, you may lose some event, but I guess for realistic shifts like beyond GR deviations or environmental effects, you wouldn't lose too much. So you can do this in post-processing.
Okay, let's thank the speaker again, and then